Okay, so so today I want to discuss more about phase transition because it's very important and it's something that we will encounter also in the rest of the class many times. And in particular, I want to take as an example the critical point that we talked about yesterday and the day before. So it's the critical point if you remember the PT plane is a line which separates solid and gas and vapor. Then there is a line that separates solid and liquid. And this line ends at a certain point. Okay? The line that separates solid and liquid can change shapes and so on and so forth, can change order of the phase transition. We will talk about this. But there always has to be a phase transition. The reason is that the solid possesses symmetries. Solid, for example, let's assume it's a crystal. Okay? It possesses symmetries that the liquid does not have. So there is in order to go from solid to liquid, you know about the symmetry groups in crystallography. You probably have heard about something. So one can characterize the crystals as being as being consistent with some discrete symmetries, which are a subgroup of the rotation and reflection groups. Okay. So a crystal has a symmetry. For example, it can have a symmetry. Take a simple crystal like the cubic crystal. Okay. It has several symmetries, apart from the symmetry of translation by one unit cell. Okay, it has also other symmetries, like if you rotate the crystal by 90 degrees, you obtain the same crystal, right? And these symmetries are not present in the liquid phase. Okay? So this symmetry have to break when you go from solid to liquid. And this breaking of a symmetry is a discontinuous process, because it's not that you can have a little bit of symmetry. Either you have a symmetry or you don't. Okay? So the breaking of a symmetry is a discontinuous process, and this leads to a phase transition. Always have to lead to a phase transition. The situation between the liquid and vapor is not the same. It's not as the differences are not as dramatic as in the case of liquid and solid, because there are no symmetries in the liquid state. There are no symmetries in the gas state. There is only a small, if you want. There is a big difference between the two things, and in fact we observe it. You know, when we see a liquid, we recognize it as being a liquid, and when we see a gas, we recognize it as being a gas. But but the difference is just in the density. Okay, the particles in the liquid are much more dense than in the gas, but there is no symmetry that distinguishes the two. Therefore, nothing prevents the situation in which you have a phase transition. The density changes discontinuously, but you can also, the phase transition can also end at a certain point, terminate at a certain point, and the symmetry changes continuously when you vary P in T. The density changes continuously when you vary P in T. This is no symmetry, as I've been saying for the last 5 minutes. Okay? So, in fact, this tri-critical point is a critical point of coexistence around which, depending on how you approach the point, you can get solid, liquid, or vapor. And this critical point here is different, because if you if you make a transition this direction below the critical temperature, then you see a discontinuous change. Okay? Let me. Hey. Okay, if I am above the critical temperature, I compress my system, the pressure changes, but there is no strange in this direction, going in increasing pressure. But here, if I do this from this temperature down, when I compress the system, my gas starts liquefying, and then it becomes all liquid, and then goes up here. Okay, so if I, so let's see. Let's put some points on this line. So this is A, B, I don't know, C, some point over here, D, and E. Okay, so I'm here. So point A is here. And then I go up, let's say on this line like this, constant temperature. So this line should be perfectly vertical. Okay, so where is point B on this line? Where? The intersection. Where is point C? Upper. So the pressure of point B, C is larger than point B. It's somewhere where? On the horizontal line, like this. So the temperature is larger at point C. But didn't we say this is an isothermal transformation? So point B is here, point C is here, and where is point D? It's still there, right? Okay, and point E then is up here. So depending, if you add a third axis to this diagram, you put the volume, then you see that essentially what you're doing is this, and then you move like this, and then come up like this. But if you don't see the third axis, these points coincide. So this is the line of coexistence. Okay, on this line, there is both liquid and gas. The precise amount of liquid and gas depends on the volume, which is not a variable in this axis here. But you can see it over here. Okay? All right. If I now cross from here, A to, let's see, E, let's jump. Then A is here, E is here, and there is no point at which this happens. Say it again, speak up, speak up. All the points on this curve have the same temperature. All the points. This point A and point E have the same temperature. Point A and point B have the same temperature. Put another point here, call it F, it has the same temperature. These are isothermal curves. It means that every point on the curve has the same temperature. Okay. So there is a particular point here, and so you see the van der Waals gas has the qualitative features of what we observe in nature. So we want to understand the vicinity of this point here, TC, VC, PC, which is this point here. Okay. And what will change between the two phases is the density. The density of the liquid minus the density of the gas. That along this line changes discontinuously. Okay? And along this line changes continuously. So if I look at this curve here, how can I get the density of suppose we are at this temperature, okay, this isothermal. How can I get the density of the liquid and the density of the gas? From? Which is? PV is equal to RT. No, that's for the ideal gas, right? This is van der Waals gas. Rho is the number of particles per volume, right? So we read the volume, and we read. So, but where is liquid? Where is all liquid at this? In this line here. B, C, or D? D. Okay. So the density of the gas here is N over B, VB. The density of liquid here, so on the same point, on the two sides of the line, is N over VD. Because if I look at VC, it's part gas and part liquid. So if I look at VC, I don't know. If I don't know which percentage is gas and which percentage is liquid, I cannot get the density of the gas and the density of the liquid. Okay? So this discontinuity here is the difference of the inverse of the volumes. N is constant, the number of particles is constant. Okay, so and here I'm considering 1 mole of the gas.
Sir, what is the source of phase transition between a liquid and the gas beside this discontinuity in the density?
Why? What? Sorry? What?
Okay. The source of this phase transition beside
the source of the phase transition.
Yeah, beside this.
What does it mean, the source?
Okay, I mean, okay, here we have the phase transition because we have discontinuity in the density, right?
Yes.
Okay. Do we have another reason beside this?
No. There is a discontinuity. If you look at the thermodynamic functions, the function which is relevant here in the PT plane is the enthalpy. Okay? And the enthalpy is continuous everywhere. Its first derivative is discontinuous. Okay? at this transition. At this point here, all the derivatives are continuous. Here, the first derivative becomes continuous. Exactly at the critical point, we will see that the first derivative becomes continuous, but the second derivative is has a discontinuity. Okay, so this is called the first order phase transition. This is called the second order phase transition. Here, there is no phase transition. But what is important is to look at the discontinuity of physical quantities like this, which is called the order parameter in this case. Although there is no order in some sense, because both liquid and gas are disordered, there is no symmetry. But in the general theory of phase transition, this thing is called order parameter. Okay? So this is the thing to look at. Okay, so let's look at the van der Waals equation. The van der Waals equation has critical pressure, critical volume, and critical temperature. Okay? Can you remind me what this is without...
A over 27 P.
PC is what?
A over 27 P.
A divided 27? B square. This is 3B. And TC is? 27R. Times something? Times B? Okay, I trust you. And I want to go back and check my notes. Okay, so let's define dimensionless variables. In dimensionless variable, this thing can be written as small p divided by 3b minus 1. Okay, now the variables p, v, and t are dimensionless. And in fact, so this means that if I measure for any substance that is well approximated by the van der Waals equation, if I measure the pressure in unit of Pc, the volume in unit of Vc, and the temperature in unit of Tc, then the equation of state should be the same. In fact, this equation is called the equation of corresponding states. So you can make a correspondence between different states of different substances if you use the appropriate units of measure. What is n? The number of particles. No. Okay, so I want to go close to the critical point. Which values do I have to choose for P, V, and T? Close to 0, close to 100, close to 1, right? So close to the critical point, okay, and actually let me write it like this. P equals 1 plus delta P, 1 plus delta V, 1 plus delta T. So at the critical point, dP, dV, and dt are 0. So if I solve this equation for P, so this equation for P is contains 1 over V squared. Instead of V, I write 1 plus delta V, and I expand everything up to and including third order in dV. Why third order and not fourth order? Because if I include the fourth order terms and fifth order terms and so forth, anything that I'm going to talk about is not going to change, okay? Because these are too small for the purposes of changing the behavior. So P becomes 4t minus 3 minus 6 times t minus 1 dv plus 9t minus 1 dv squared minus 27 half t minus 1 dv cubed. Uh, 27 half t, I think that's really not correct. I think this should be 12. I think I have a mistake on my notes. But anyway, the following one is correct instead. So when t is close to 1, this becomes 4 delta t. This becomes dp. This becomes 1 plus 4 delta t, and 1 is just cancelled by the p minus delta p. So this is 4 delta t minus 6 delta t delta v plus 9 delta t delta v squared minus 3 half delta v cube plus blah blah blah. Okay. Here I'm neglecting order delta t delta v cube. I'm neglecting it. So why is this? Because and also let me show you that we can neglect this term here. We can neglect delta t delta v squared. Why is this? Because I will show you that the relevant region where things happen is where delta v is of order of delta t to the 1/2. Actually, let me. Because, as I said, delta v will be smaller or of order of delta t to the 1/2. So if dv goes like delta t to the 1/2, then dt dv goes like delta t to 3/2. Delta v cube goes to delta t to the 3/2. Delta t dv squared goes like delta t squared. Okay, 1 plus 2 times 1/2. And it's smaller or larger than delta t to the 3/2? Hmm? Should we have a pool, like, let's vote? It's smaller, because delta t is small, so delta t squared is smaller than delta t to the 3/2. This thing goes like delta t times delta t to the 3/2, delta t to the 5/2, even smaller, and this one is this one here. So this term here, so I make an hypothesis. The hypothesis that the relevant scale will be delta v to the delta t to the 1/2, and then I will show you that this is true. So under this hypothesis, I can drop this term here. Okay, so let's plot this function here. So first of all, for delta v equal to 0, it's always delta p equal 4 delta t. So if delta t is larger than 0, we have a function like this. Okay? If delta t, so if delta t is equal to 0, the function goes to 0. The first, second, and third derivatives, the first and second derivative are 0, because we have 0, the value of the function 0, minus 0, and the only term that survives is that. So this is delta t larger than 0. Delta t equals 0. And when delta t is smaller than 0, the sign of the derivative of the origin changes and becomes positive. Well, here it was negative and here it was 0. So the function goes like this. But then eventually delta v cube always wins. So the function does something like this. The intercept is always delta p equal to 4 delta t. And the function is symmetric with respect to exchange of delta v with minus delta v. Okay? Let me actually. All right, so what are we doing here? We are just plotting the van der Waals equation in a new set of coordinates where we have shifted the origin of the pressure and volume, and we put it over here, okay, and temperature. And we are neglecting things which are negligible in the sense that I showed you before. But this is still the van der Waals equation. And as you know, we have to do Maxwell construction. Okay, so actually, this is gas. I follow it up to a certain point here. Okay, and then I start generating liquid. Up to a certain point where all the liquid is all the substance is in liquid form, and then it starts being liquid. So now I have to do the construction in which I have to evaluate the area under this curve and impose it that it is equal to the area under this curve. But here we have there is a much smarter way of doing this. We have to achieve this, but there is just one observation that one can make and just find this point straight away. Can you see it? So this is something that we have been saying for like 3 or 4 lectures, that you have to. How you plot this? Okay, this is the equation that you have to plot. This is a cubic polynomial. By the way, if you don't have, if you are not familiar with plotting polynomials, you really should do it, because in the exam there will be a lot of it.
Yeah, because when I show your graph, function of delta p and delta v.
This is delta p as a function of delta v.
So I think I should plot delta p function of delta v.
That's what I'm doing. What's not convincing you? I'm plotting delta p as a function of delta v. You plot the function here and the variable on the x-axis. Okay? So, let me repeat for the millionth time. You have to go home and exercise on these kind of things. Functions, plotting the function, taking derivatives, integrals, okay? You have to know how to plot you need to know how to plot a polynomial, what it means that the derivative of a function is 0 in the origin, it's not 0, what's the intercept of the function with the y-axis, and so on and so forth. It's very important. Okay, let's go back to this thing here. So I want to find now the reduced volume of the gas and the reduced volume of the liquid.
Yeah, I think if we see that the width is like the intersection of if we take the first curve and
What is the first curve?
I mean,
With this curve here?
no, the one that's the former curve.
This?
dt is dt greater than 0.
No, dt greater than 0, there is no Maxwell construction.
Yeah, but I mean the line is such a, the width is like same as.
Say it again.
Okay. For dt greater than 0,
Uh-huh.
dp intersect dv at some point.
Yes, here.
Yeah, and then for dt less than 0, it intersects somewhere here. And the width
Here?
is, no, okay, dv, line dv.
Oh, here?
Yeah, and then the width is like va minus l.
No, because with
If it's symmetric,
yes,
just a line which
yes, very good, very, very good. That's the correct answer. If the curve is symmetric, if I trace a straight line that goes to the origin, that goes to the intersection point, by construction, this area is equal to this area because it's symmetric. Okay, so the important piece of information is the fact that in these coordinates, the curve is symmetric with respect to exchanging v and dv in minus dv and flipping dp. So I don't have to do any Maxwell construction. I mean, I have to do Maxwell construction, but I don't have to calculate any integral. I just trace a line at 4 dt, okay, which is where dt is negative now, and I get the intersection points. So I have to solve the equation 4 dt is equal to 4 dt minus 6 dt dv minus 3/2 dv cube. Okay, so this is equal to 0. So the three solutions are clearly dv is equal to 0, but this is this intersection point, we are not interested in it. And then dv 1, 2 is equal to let me do this. This is equal to minus 6 dt dv so it's plus or minus 2 square root of minus delta t. Okay? So, the difference in the specific volumes is V, it's delta V, which is V gas minus V liquid, is 2 times this object here. Let's remember that the scale was Vc, because we divided by Vc. Okay, and so this is square root of minus Tc minus T, actually Tc minus T divided by this. 2 times 2 is 4. Now the change in density, actually the variation of the density is minus the variation of the volume divided by the volume squared, right? If dV is small. And by the volume we can just put Vc squared. So the change in density is, okay, now if we define the change in density as the density of the liquid minus the density of the gas, we get rid of this minus sign here. So this is 4 divided by Vc. So if I plot the change in the density, the difference in density between the liquid and the gas phase, this goes to 0. If I increase the temperature in this direction, okay, and then goes to 0 at T critical, like a square root, with the coefficient in front, which is not important, and then stays 0. What? Why is it half of what? Oh, sorry, it's not half. I meant 1 or 2. Delta V 1 or 2 is plus or minus. Where is? No, it's 4 because it's 2 minus minus 2. Okay, so if we go back to this diagram here, so when we cross so look at this line, we can look at the temperature, we project it down, we look at the temperature on this line, then the difference between the part above the density of the substance above this line and below this line is always zero, is always non-zero, sorry, and goes to 0 when you approach the critical point. When you approach the critical point, it goes to 0 like Tc minus T. d rho or dV, it's called the order parameter because if it's yeah, okay, we'll see more examples of these things. So later, it makes more sense when you're talking about order. Here, you're not talking about order. They're both disordered phases, as we say. It's liquid and gas. But the analogy with situation in which there is some order that breaks down, a discrete symmetry that breaks down, like in the case of magnets, we'll see. That's why this is called the order parameter. Okay. Is this clear? Okay, so let me recapitulate. When the temperature is higher than the critical temperature, what is it? Delta T larger than 0, delta T less than 0? What do you think? Larger than 0. because he said so, because you had to. So it's larger than 0, right? Because this is t divided by tc is larger than 1 if delta t is larger than 0. So this is the supercritical region, super, above, okay, above the critical region. When delta t is equal to 0, t is larger, smaller, or equal than tc? Is equal to tc. Okay? So it's the critical region. Okay? When delta t is less than 0, it's larger, equal, or smaller than tc? It's smaller. Okay? So when t is larger than tc, we see no distinction between the liquid and the gas. There is only one substance. Okay? When you change the pressure or the volume, I mean, you can only change one of the variables. In this range of temperatures, you don't see anything strange happening. Just, you know, you can compress the substance. And when delta t is less than 0, temperature is less than the critical temperature, you see a phase transition. As we saw yesterday, there was a line in the video. There was a line. Below the line, there was liquid. Above the line, there was gas. Because for Archimedes' principle, things that are denser, they go down. Okay? So the liquid was down, and the gas was up. Okay, very good. So when the volume is large, we have only gas. And then you start compressing the volume, you reach here, you start generating some liquid until you are here and you get all liquid. Now, the difference between these two situations is that in one case you see a discontinuity between the density of the liquid and the density of the gas, because there is a finite distance between these 2 points during this process. And here you don't have this finite distance. There is no way to identify here where is the gas, where is the liquid. Okay? We computed this distance in density as a function of the temperature. And we saw that it's a small change in density between liquid and gas when you go close to the critical point. And in fact, it vanishes exactly at the critical point. This is equal to 0 when t is equal to tc. This, tc, t. This square root is quite important. Okay, we will see later on how this square root of an ordered parameter comes up. Okay? Is it a little bit more clear now? Okay. Now let me do another calculation. So the idea is the following: that the two phases are the same above the critical temperature, and they are distinguishable below the critical temperature. The two phases, liquid and gas, are the same above, and they are different below. And another indication for this is if we calculate, if you use Clausius equation, Clausius-Capeiron equation, we call it Capeiron equation, which says that dP by dt is the latent heat of vaporization divided by T divided by delta V. Okay? So here we saw what happened. So this equation has only sense below Tc, because we have vaporization below Tc, where the liquid and the gas comes out in equilibrium. So dP by dt, let me write this as P critical dP divided by T critical dt. I'm just changing the units. But, sorry, d dP divided by d dt. But delta P is equal to 4 delta T for T less than Tc. Okay, we saw it here. You reach delta P equal to 4 delta T because of Maxwell construction, then P stays constant. Okay, so d delta P by d delta T is equal to 4. So this is equal to Pc divided by Tc times 4. Okay. On the other hand, here we have lambda divided by T. So lambda is equal to T Pc divided by Tc times 4 times delta V. Delta V being, sorry, okay. Now for T close to Tc, we can just substitute this by Tc. So this goes away. And this delta V, we got it from here. So this becomes 16 times Pc Vc square root of Tc minus T divided by Tc. Okay? So what happens to this equation when, so this is the vaporization heat. The heat that is necessary to vaporize a mole of substance at this temperature. So what happens when T goes to Tc, to this thing here? It goes to 0. What does it mean that it goes to 0? That you don't need to do any work. You don't need to give any heat to the system in order to vaporize, to send liquid into gas. Because they are the same substance, the same phase. They are becoming the same phase. So lambda goes to 0 when T goes to Tc. So the densities become the same because the difference in density goes to 0. It does not require any work to transform one into the other. Okay. Now, in the last 20 minutes, is this clear, first of all? Because this is important. I mean, you need to sit down and really think thoroughly to this concept because it will occur many, many times. Okay? If you don't understand it, it's important that you keep trying to understand it, at least. Okay. We will see simpler examples of this. I'm sorry we have not addressed magnetic systems. But I think in magnetic systems, these concepts are there and they are even easier to understand because you can talk, instead of talking about change in volume, you can talk about change in the magnetization of the two phases. You can have a system which is magnetized in one direction or the other direction. And when you approach the critical temperature, the Curie temperature, this is called Curie temperature, then your system, the two phases stop being magnetized. There is no magnetization difference between the two phases, and the system becomes one single paramagnet. Okay. Let me erase this. So, as I said, when we are talking about constant pressure and constant temperature, the relevant thermodynamic potential that we have to use is phi, which is a function of pressure, temperature, and we now use as a free parameter the difference in the specific volumes of the two particles, of the two phases, sorry. And we impose that this is achieved as an equilibrium condition. Okay? In fact, as you know, if your system has a constant pressure and constant temperature, it has to reach the minimum of the enthalpy. And the minimum is achieved when the derivative is equal to 0. You also have to require that the second derivative is positive, okay, in order to have a... So this equation has to be equal to the equation that links the pressure, temperature, and delta V. So if we now use the same coordinates that we have used before, and instead of talking about pressure and temperature, we could talk about delta P and delta T. Okay? Then this has to be equal to okay. No, there was a minus. Oh, okay. I'm just using the wrong signs. No, that's correct. What did I use? Okay, so I want this to be positive, this has to have the opposite sign, and delta T has to have the opposite sign, so... Right? Okay. Hmm? No, because this, if you put this equal to 0, then delta P is equal to 4 delta T plus 6 delta T. It's minus, okay. Okay, let me skip this thing here. Let me just write. Let's do this, okay? Because I didn't write the intermediate passage. I wrote this thing here. So phi. Let's take phi of P, T, and delta V as being a phi 0. Now we reconstruct the sign, the correct sign, okay? minus a constant, let's call it small phi, because everything is dimensionless, so this has to be the dimension of an energy, minus delta P minus 4 delta T times dV, minus 3 delta T dV square, plus 3, 8 delta V to the fourth. Okay? Now let's take d phi by d delta V, and this is a constant. Minus delta P plus 4 delta T minus 3 delta T minus 6 delta T delta V square, delta V, sorry, I'm taking derivative, plus 3 half delta V cube, and this had to be, sorry, this has to be, okay. So here is the difference, right? Because we had, this was negative and this was negative as well. Okay. Okay, is it correct now? Okay, we reconstructed all the minus signs. Okay. Okay, very good. So when I set this equal to 0, then I get the equation for that links dp, dt, and dv before. But now let me look at this function here of delta v. This function here as a linear term which we can write as phi 0 delta p minus 4 delta t times delta v. Okay? Then it has a quadratic term which is 3 times phi 0 delta t delta v square, and then it has a quartic term which is 3/8 times phi 0 delta v to the fourth. Okay. So look at this function. We have to look at this function when delta v is small, right? If delta t is positive, forget for a second about this term here. Let's put delta p is equal to 4 delta t. Okay? If delta t is positive, then this function looks like a parabola in the origin, like this. And we say that we have to minimize this function. And the minimum of this function is at delta v equal to 0. Okay? So I'm looking here at dp is equal to 4 dt here, and I get that delta v is equal to 0. It's the minimum of the enthalpy. It's the equilibrium state, because we said that the equilibrium state for constant pressure and temperature are obtained minimizing the enthalpy. Now, I'm assuming that this is equal to 0. If this is not equal to 0, then we still have a single minimum if delta t is positive, only that it's going to be a little bit shifted. It's shifted to the right or to the left, depending on whether this term is positive or negative. So you can have something which looks like this, okay, or something which looks like this. But still there is one minimum. So delta t larger than 0, single minimum let me erase this thing. Is it clear? Have you ever studied the minima of function? Simple polynomials? Yes. Okay. So when delta t is negative, so actually let's look at delta t is equal to 0. Again, let's consider this term here equal to 0, because I can adjust the pressure to be whatever I want. Okay, so delta p is equal to delta p minus 4 dt is equal to 0. Delta t is equal to 0. My function looks like this. It has a very flat region here around delta v equal to 0. In fact, the first, the second, and the third derivative vanish. I'm only left with this quantity. The only thing that does not vanish is the fourth derivative. So the function is very flat. But there is still a single minimum. Okay? If delta t is less than 0, how should I draw this function? What do you think? No, you. Yes.
Okay, I go back in my question.
Which question? How do you draw this function? That's the question I'm asking you. So you asked me and I'm asking you. If delta t is negative,
This will be positive.
hmm?
Delta p plus 4.
Phi 0 you can put it to 1, doesn't matter. It's just a positive quantity. So qualitatively, if delta t is less than 0, okay, and this term here, again, drop it, equal to 0, doesn't matter. So I'm asking you how to draw this function here, which is the sum of these two terms. I want you to draw the function y is equal to minus x squared plus x to the fourth.
Okay, so I can put x squared outside. Okay. Or
Sure.
I take the first derivative.
Okay?
The first, and then I will take the second
Uh-huh.
derivative, and then I will see the sign of the second derivative.
Okay. Where? So the sign of the second, okay, let's look at the first derivative. Where? With the value where? For which value of x?
No, I will take 0. The first, and then I.
You take the first, then you put x to 0. And what is the result?
0.
0. So how should I draw this function?
Okay, so it is positive. Okay, the first derivative is positive.
No, it's 0.
0. Okay. So in 0.
It's a very peculiar positive number.
If you want, I can count to.
Sure. No, it's because of the blackboard of the cameras. I'm not sure if you want to be.
Okay. z prime we will call minus 2x plus 4 x cubed, okay?
Mm-hmm.
So if I need the sign of this is equal 0. This means I will get plus 4 equals 0. I will get this 2x squared minus 1 equals 0. So I have 2 points, x equals 0, okay, and x equals plus or minus 1. Okay, so the first derivative will be called 0 for x equals 0, and for x equals this.
So how can I draw this function?
Okay, I know for x equals 0, so for x equals 0, I will get this point here. And for x equals 0, because I have 2 points.
Okay.
X equals 0, and then for x equals plus minus 1, and I think I have a 2 of 2. This is all time will be called positive.
This is what? Sorry, say it again.
This will be positive. No, negative. This negative. Okay.
But I don't want the precise numbers. I just want a sketch of the function.
Okay.
How does it look like? Does it look like a circle? Does it look like an
No,
ellipse?
Like
Does it look like?
it will not like this. Something like that.
It will be like this.
Yes.
So you found 3 solutions to the derivative equal to 0. Where are so one point is here. Where are the other 2?
The two, this and this. What do you mean?
You solved the equation y prime is equal to 0,
Yes.
which means that which points are those for a function?
No, x equals 0, and then x equals plus or minus 1 out of 2.
Okay, these are 3 points.
Yeah, sure. So this I can find it also. The image of the two.
But what are these points where the derivative is equal to 0? They are called? They have a name. They are called stationary points. Maxima, minima.
Ah, okay. Stationary point? No, I don't think so.
I don't think so. No, I'm telling you. They are called stationary. Believe me.
Maximum and minimum point.
Yes. They are called stationary points. Maxima, minima.
Maximum and minimum points.
Okay, so we don't have a plot for this function. We know it has 3 maxima and minima, but we don't have.
No,
You just draw it. What do you expect? So
okay, let me do it. First here, okay. Okay, let me take this. I can take when I will replace.
but look, if I put here 27 instead of 1, does the shape of the function change?
Yes, it's 0 is 0. 1 point, okay. Yes, the second point will be, because this is all time for those points, all time will be negative.
Okay.
So the second point can be here.
All right, so let me do this, because we have very little time, so you have to go away. So let me do this. So when you see a function like this, the first thing you look at is where are the maxima and minima. If there are, and where they are is not important, how many there are. Okay? There are 3. Okay. So there are 2 minima and 1 maximum. Why? It's a local maximum. It cannot be a global maximum because x goes to infinity, this function goes to infinity. Okay? So there is 1 maximum and 2 minima. And the function goes like this. Actually, let me. Okay? So this is the local maximum, and these are the local minima. There are two of them. Okay. And in fact, if you solve for these two local minima, you find the density of you find the two solutions of this thing here. dV of the gas and dV of the liquid. So please do some exercise, because it's not possible in order to draw on the blackboard a qualitative sketch of the function minus x squared plus x to the fourth. You have to find all the derivatives of the function. You have to know these things by heart. Okay? Okay, so for delta t less than 0, instead of a single minimum, we have two minima and one maximum. Okay, so these two minima correspond to the density of the gas and the liquid phase, which are the stable phases of our solution. If I change dp minus 4 dt to positive or negative, what I do is I do not change the number of minima. Okay? The only thing that I do is I tilt them. So this goes down and this goes up. So one becomes more convenient than the other. One becomes the here for dp is equal to 4 delta t, the two minima are degenerate. They have the same value of the enthalpy. So I cannot distinguish between, I cannot choose between them. They coexist. When I change delta p minus 4t, so I'm applying a pressure to the system. Okay? I can either, if delta p is positive, then I'm applying more than p critical. If delta p is negative, less than p critical. Then my system goes into gas or a liquid phase. Okay? And in fact, in order to move away from this line, I have to go away. Because here, delta p is equal to 4 delta t. So I have to go away to this point here. Or, if dp is larger than 4 delta t, I have to go up here. And you see here you have only liquid, and here you have only gas. Okay, so the critical point that we are describing is obtained by looking at the behavior of a function of a single variable delta v and two control variables, temperature and pressure. And I have to look for the minima of the volume, of the enthalpy as a function of the volume, for a given pressure and temperature. And there is all the qualitative description of the critical point that we have looked so far. Okay? Okay, let me stop here.